In this video, we're going to talk a little bit about some design decisions that need to be made around the 16-bit instruction format. This one's another The World According to Adam video. The decisions we make here are going to be crucial for the computer build going forward.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
So my 16-bit instruction format starts with a 4-bit conditional execution. This conditional execution is modeled after the ARM architecture. And that's based on whether or not flags are set. So if you have a branch and load, speaking of ARM, branch and load on carry, when carry is set, then if you have a carry condition, you can execute a subroutine, for example. Then there's 8 bits of instruction, and those are going to be allow up to 256 different variants of instructions, and those will also encode the target register for any given instruction. Now, that's not to say that I'm going to have up to 256 different instructions, and then with 16 different registers, I've got quite a few things that I've got to consider as far as how many instructions I can really genuinely allow. And then at the end of that, there's 4 bits of parameter. Now, I'm choosing to put the parameter that is going to be output on or asserted onto the bus and encode that as part of the instruction. Basically, the EPROMs that are used to convert the instruction into a control word are incredibly slow. And so by encoding the piece that gets asserted out onto the bus into the instruction, that allows me to bypass some of that, get the data out onto the bus a little bit sooner. That way I need to only worry about the latch timing in the decode. And hopefully that gives me the ability to run things a little bit faster. It's a bit of a risk, and I understand that, and I'm trying to work through exactly how all that's going to work. So not everything is cast in stone just yet. So the flags that I've got available to me, I want to have a 0 flag, a carry flag, a negative number flag, meaning I've got, if it's a signed integer, I've got a negative number. And that's effectively if the highest order bit is set. And then an overflow flag. And calculating the overflow flag can be somewhat difficult. And I've got a link up here to a website which describes how to do that. And we'll have to figure that all out in the ALU. But using those conditions, I can then encode for any given instruction if statements, basically. So I can now branch if some condition is true. Having those flags immediately available then allows me to have the conditional execution with just about any assembly language opcode. So I can add if carry is set. I can subtract on less than or equal to, or I can do shifts based on whether or not carry is set or an overflow has happened. So from that perspective, it, I believe, opens up a whole realm of additional possibilities here for instructions. Now, this is modeled after ARM v7a Architecture Reference Manual, or ARM, and it's section A8.3, if you care to go take a look at that. Given the test conditions that are present, I'm wondering if it doesn't make sense to add an L flag, whether or not there's a signed less than condition, meaning that if and only if the negative flag is not equal to the overflow flag. And that if that happens prior to the flags being latched, then that reduces some of the latency in evaluating the condition on whether or not it's been met. And then on top of that, even further, I'm also wondering if I should store inverted copies of each of those flags to make it easier again for doing comparisons. So the instruction format is as I had before. So my control table lookup, which is which signals are going to be active at which parts of each of the instructions. The low order 8 bits, I'm looking at having the actual instruction itself. And then the next bit up above that is whether or not that condition has been met. I'm not totally certain I'm going to encode that into the instruction yet. I may use that then to turn on or off the output of the latched control word. And if I turn off the latched control word, then effectively with all those bits off, it becomes a no-op. And that may be a faster way or more reliable way of evaluating that condition such that I can control the execution. Now, that said, I've got a placeholder for it right now in the instruction or control label lookup. I do plan on having a context indicator in the flags register. That context indicator is going to be whether or not it's in program or application mode or interrupt mode. And that's simply going to be a flag that's hard coded to 1 or a 0 based on which mode you are in. Now, that means I'm also going to have a shadow copy of the flags registered so that on interrupt, you switch from the application flags to the interrupt flags. And that should then preserve the application flags. I'm also planning on having a swapped PC and return address register, so they're going to bounce back and forth between the two. James Sharman did something very similar in his architecture, and I plan on modeling that as well. And at the same time, during an interrupt is going to have its own stack and its own program counter. So with that being said, I end up having 3 additional registers that I need to keep track of. And there are 4 bits that are unused at the moment, so I think I have some room for expansion and some room for growth. So that then expands our flag register now to include whether or not an interrupt is pending, which will come from the interrupt controller. I'm putting a placeholder in that right now. And then whether or not interrupts are enabled, again, that's going to come from the interrupt controller and be latched on every cycle just to make sure that things are actually being latched and held properly. And then the context flag, which is hardwired, depending on which flags register is actually active at the moment. So again, there's just, flags are read-only. You can't directly manipulate them. There may be instructions that do that, but you can't directly manipulate them. A couple shadow copies of the flags register, shadow copies of the program counter and stack register, and then of course there are swapped versions of those so that you can bounce back and forth between the two. Issuing an interrupt will change the context, and that will be both a hardware and software interrupt. And then returning from an interrupt, if I have an interrupt return instruction or the like, will force the context back to programs. It's not going to do any checking. If you do an interrupt return from an application context or program context using those terms interchangeably, it's not going to do any checking. It's basically going to set the context back to the application context and therefore use those registers. So this then updates our clock cycle definition. And the 2 things that I've added now are highlighted. I'll start on the right. Latching the flags is going to happen the same time we latch new values. But on the left, the control ROM resolve, which is how the address, this is the one, that 150 nanosecond latency, the time it takes to resolve that control word from the control bits that go into it, the instruction and any of the other bits that are set, is going to take some time, and I'm anticipating that that's going to happen on the high level. We want to have that resolve as quickly as possible so that we can latch what that control word is. Now, I do have concerns. My first red flag here. I do have concerns about the timing and the resulting speed. Remember, my goal is to have this running at better than 10 megahertz if I can manage to pull that together. And so I'm concerned about what the resulting speed limitations are going to be. That said, stay tuned. We're going to have to build out enough of this to test to see just how fast we can go. And we'll have to do that relatively quickly. So next up is going to be assembling at least one of the 16-bit PCB registers and get that integrated into the build. Now, there is a component of this that I did not consider quite yet, but we'll have to do some research and figure out how I'm going to handle it. The TTL outputs are compatible with CMOS inputs. The CMOS outputs, on the other hand, are not compatible with TTL inputs. And I believe there's a way you can handle that by using pull-up resistors and the like, so I'll have to figure out exactly how I'm going to get that wired up. And then the clock issues have been resolved, but I still want to run through a KiCad clock circuit design. Even though this is version 1 is not going to be the final version, I do want to design that up and may end up putting that onto a printed circuit board anyway. I haven't made a decision on that yet. And then I still have to add a line driver to the bus input test harness. I'll probably hold off on building that until there's an actual need. So these design decisions are going to guide us in building out our instruction set and as well as building out our control word and our control module. Thank you, and we'll see you soon.